So what we have here on the top of this page is a nice visual representation of what we just talked about. When can you say it's continuous and include the point A and B with brackets rather than not include it? It says the function f is continuous from the right at A and continuous from the left at B. In other words, we can use the brackets if it looks something like this right here. It says similar definitions can be made to cover continuity of intervals of the form where one of them is closed and one of them is open. So for instance, what if we had something like this right here where this was an open circle here but had a closed circle down here? So at A I've drawn a closed circle that doesn't match, so the function value doesn't match the limit value there. This is when you would do something like a parentheses A because it is not continuous at A to the point B, and then B we could use a bracket. So that's what something like that would look like right there. Okay. So determine the intervals of continuity of f of x equals 1 minus x squared. So what you need to remember for this is anything underneath the radical must be greater than or equal to 0. So we're going to solve 1 minus x squared is greater than or equal to 0. If you did the lines and functions review on this before this class, you realize that this is a quadratic inequality, and the way that we do quadratic inequalities is you always want to set things greater than or you always want to factor it and set each factor equal to 0. Well, this is actually a difference of squares. This is 1 minus x and 1 plus x. Set those factors equal to 0, so that'd be 1 minus x equals 0 or x equals 1. This would be 1 plus x equals 0 or x equals negative 1. And so the idea is here you have the points at negative 1 and 1, and you want to know when is this positive. This is where you do the test points. We know it's 0 at both of those points. We have to look at the opening interval, which is negative infinity to negative 1. You would look at negative 1 to 1 and also 1 to infinity. You'd choose a test point. Once again, we're plugging it into the function 1 minus x squared, or you can plug it into the factored form. You pick a number in each one of those intervals. So for instance, negative 2 is in the left interval, 0 is in the middle, and 2 is in the right interval. If I plugged in negative 2, it'd be 1 minus negative 2 squared. That would be a negative number, so it's always negative in that interval. If I plugged in 0, it'd be 1 minus 0, which is positive, so it's always positive in that interval. And if I plugged in 2, again here, 1 minus 2 squared would be a negative number, so it would be negative in that entire interval. And remember, we were looking for when is this function positive, so it is positive on the interval negative 1 to 1. So that's where this function is defined, on the interval from negative 1 to 1 with parentheses. So we know it's continuous on the interval negative 1 to 1. The question is it continuous with brackets at that point? So you would have to look at what's the limit as x approaches negative 1 from the right, and what's the limit as x approaches 1 from the left of this function. In doing that, we could do it multiple ways. We could use the table, plug in numbers just to the right of negative 1, like negative 0.9, negative 0.99, negative 0.999, and just to the left of 1, like 0.9, 0.99, 0.999. See what our values are. You could also look at the graph. The graph again here is a circle. The top half of a circle is centered at 0 with an x values of negative 1 and 1. You can see that this function is continuous, that the function value is 0, that the limit value is 0. So it is continuous at that point from the right for negative 1, and it is continuous at that point from the left at 1. So we can include those points. So that would be bracket negative 1 to 1 with a bracket. What's the real answer? Anytime you have a radical, at least square root, as long as it's in the numerator. If it's in the denominator, it's undefined when it's equal to 0, so you can't include it. But if it's just a radical, like the square root of 1 minus x squared, you can go ahead and say that it's continuous on that closed interval. You don't need to do all the math. If you read up here, you can see it. They give you, here's x is continuous on bracket 0 to infinity. 2 minus x is continuous on negative infinity to 2. Again, the way they would have gotten this is they would have set 2 minus x is greater than 0, greater than or equal to 0, and you can include that endpoint. This one was a little more difficult because it is a quadratic function. So that's where it comes down to. So let's look at properties of continuity here. Properties of continuity. It says if b is a real number and f and g are continuous at x equals c, then the functions listed below are also continuous. We can multiply it by a constant. We could add or subtract it. We can multiply them or we could divide them as long as it's not equal to 0. Again, this comes directly from those limit rules that we talked about last time. Take that constant out in front, separate addition and subtraction. Multiplication, just do each one individually, and division, just do each one individually. This is directly from the definition of limits or limit rules. It extends to the properties of continuity.